So the thermal expansion التمدد الحراري is an increase in the size, increase of the volume of the material of a substance when the temperature is increased. So when you increase the temperature of a substance, this will increase the kinetic energy as we said before. So the kinetic energy also will increase. This increase in the kinetic energy will cause more collisions. It will cause more collisions with higher energy. So the particles will move away from each other. Okay, they will move away from each other. This will increase the distance in between, and totally it will increase the size or the volume of the material. So increasing the temperature leads to increasing the volume. What about the density, الكثافة? Density, if you remember, it's mass over volume. Usually we give the density the symbol rho, the mass the symbol m, and the volume big V. So we can say density equals mass over volume. So we can find this relation directly. The density is inversely proportional to the volume. Density is inversely proportional to the volume. So if the volume increases, the density of the material will decrease. Okay? So these are very important relations. The thermal expansion, we can find it in the thermometer. There is a reservoir here, a small reservoir of mercury or alcohol. They have a good thermal expansion coefficient. So when you heat it up, so when you increase its temperature, it will expand. This container or this reservoir is attached to or connected to a tube, a small tube, this one. So the elements of alcohol or the particles of alcohol will move inside this tube until it reaches to a certain point. This point is calibrated to give you a certain temperature. So that's a thermal expansion of the mercury or alcohol in the thermometer. Also here in the balloon, the increasing of temperature, they heat up the gas inside. They heat up the gas inside. So this heating up of the gas will increase the temperature of the gas. This will increase the kinetic energy. So it will increase the distance between the particles, and this will decrease the density of the gas inside the balloon. So inside the balloon, the density is lower than outside, and this helps the balloon to move up. So why the balloon moves up? The balloon moves up because the density of particles inside the balloon is less than the density of air molecules outside the balloon. Why is that? Because the temperature inside the balloon is higher than the temperature outside the balloon. And they do it by a heat source. They use a heat source to heat up the gas or the air inside the balloon. Okay? It's working for the materials. While the water, it has a strange behavior between 4 degrees Celsius and 0 degrees Celsius. How is that? Let's draw a relation between the temperature and the density of water. Let's start from 20 degrees Celsius up to 100 degrees Celsius. At 20 degrees Celsius, let's say the density is whatever number. When you heat up the water, you increase its temperature. And we said when you increase the temperature, what happened to the density? The density will decrease. So the density of the water decreases until you reach to the 100 degrees Celsius. So when you increase the temperature, density will decrease. So we expect also when we decrease the temperature, the density will increase, which is fine. But actually that's happening. It's normally happening. So if we are at 100 degrees, This is the density at 100 degrees. If you decrease the temperature of water, its density will increase. If you put, the density will increase. But this will happen until you reach to around 4 degrees Celsius. So until 4 degrees Celsius, everything is fine and it works, the thermal expansion works fine. But below the 4 degrees Celsius, there is something else happening. Here, this is water. The water molecules, they have random motion, and the distance in between those molecules is like random distance. But when you freeze the water, so below 4 degrees Celsius, the water will start to form, or the water molecules will start to form crystals. It becomes a crystalline solid, if you remember from last lecture. It will change from random shape into crystalline shape. Okay, so these molecules will form a stable hexagonal crystal structure. And because of this shape, there is a big distance between the molecules. Look at the distance in the middle, in the center of this crystal, there is a big space. There is big space. Okay, so the space between the molecules in the crystal, it will cause the whole volume to increase. So this will cause an expansion. So although you are cooling it down, you are lowering the temperature, but the volume will increase, causing the density to decrease. So below the 4 degrees Celsius, we will see that the density decreases. Okay? Again, why does the density decrease? Because water molecules, they are arranged in crystals. The space inside the crystal is way bigger. Okay? It's not the random particles or the random molecules of the water. No, it takes a hexagonal shape. So this size of the hexagon crystal will increase the size of the ice, and it will cause an expansion. And of course, expansion means the volume increases or density decreases. That's why if you put a bottle of water, if you have a bottle of water, and you fill it with water, and you tighten it, then you put it in the freezer. Put it in the freezer and leave it for like 6-8 hours. After 6-8 hours, all the water will freeze and they will expand, causing the bottle to crack. This will break the bottle, especially if it is glass bottle or something like that. Okay? It will break because the water inside turns to ice, and the ice has a size bigger than the water, and this will crack the bottle. Another question, why the ice floats in water? Because it has lower density, because ice has lower density. Why does the ice have lower density? Because it forms crystals, and the crystal size is bigger than the random size of the water molecule. Okay? So let's move to something else. The properties of fluids. What do you mean of fluid? Fluid means مائع. It's whatever substance that can flow. Substance that can flow, we call it fluid. Like gases, like liquids, like plasma. Plasma also, because it's originally plasma is a gas, but it's ionized gas. Okay? So because it's in the gas state and then we ionize it, so it's also flow. It can flow, so it's called fluid. Muhammad asks, so all states of matter are fluids except for solids? Actually, even in solids, sometimes the solids are fluid. Like let's take the concrete, for example. Concrete. Kharasana. Concrete is like a mixture of what? Mixture maybe of sand, cement, granules, water, and maybe some other additives. Overall, if it is wet concrete, it behaves like a fluid. Okay, so the wet concrete, although it has sand, which is a solid, and cement and granules, okay, but overall it flows as a fluid. Okay, so it depends on the state if it can flow or not. The objectives of the lecture today is to study some properties of the fluid. What is the buoyant force of the top? The Pascal principle and the pressure in the fluid, the Bernoulli principle, and the viscosity. Viscosity اللزوجة. Okay? So starting with the buoyancy of puffing. What is buoyancy? If you play, let's say you play football, and the ball, maybe you will throw it in a pool or something. What happened to the ball when you throw it in the water? As you can see here, some part, the lower part of the ball will submerge. يغمر. This part will be submerged under the water, while the whole ball will be outside the water. And the ball floats. The ball floats. Okay? Why is that? Because we have the weight of the ball downward, but also we have another force upward. This upward force, we call it the buoyant force. Buoyant force, okay, guys? So this ball now is under two forces, the weight of the ball and the buoyant force. Let's try to hold this ball, hold it by your hand, and try to push it down. Try to push this ball down. What do you feel when you try to push it down inside the water? What do you feel, guys? Do you feel more resistance or less resistance?
More resistance.
More resistance, that's right. So, as you say, you will feel more resistance. So, when you try to move the object inside the water, you increase the volume under the water, or you increase the submerged المغمور, submerged volume under the water. So this will cause the upward force, which is the buoyant force. The buoyant force to increase. Okay, guys? So we can deduce roughly that the buoyant force, I will call it BF, depends on what? It depends on the submerged volume of the object. The submerged volume of the object. If there is small volume, there will be no force. But if you submerge more volume, the buoyant force increases. That's why if you try to push it down, then suddenly you leave it, what will happen? It will move up. Okay? Okay. This guy here, this young man, let's say he is holding a certain object under the water. So most of the volume is under the water. Most of the volume of the object is submerged. So this will cause a big buoyant force. So there is big buoyant force. So the water, as we say, the water helps you to carry the object. Okay? But when he moves outside the water, so now the part of the object under the water is less. So the submerged part of the object is now less than before. So the buoyant force becomes smaller, and then you will feel the weight of the object. Okay, guys, so again, the buoyant force depends on what? The submerged volume of the object. And that's what Archimedes found when he studied the buoyancy. What is the buoyancy? The definition of buoyancy is the ability of a fluid, which is a gas or a liquid, to exert an upward force against gravity. An object that is immersed. Immersed means submerged. more. Okay, and by immersed or submerged, this might be partially, or fully. Partially or fully, guys. Partially means what? What does this mean? So part of the object is under the water, part of the object is above the water. That's partially. Fully is completely under the water. So fully submerged or fully immersed, it means the whole object is under the water. Okay? Like in case of the ball or in case of the bag that this boy holds. Okay. So the buoyant force on an object equals what? Equals what? Let's see. Here I have an object of a weight W, and when we weigh the object using a spring scale, we found that the weight is 20 Newton. The real weight of the object is 20 Newton. Then we will try to submerge it in water. We will fill the tank. We will fill it to the top here with water. Then when we put the box or when we put this block inside the water, first the water will overflow. It will overflow. So the water, the overflow will move and we can receive it in this cup. This is what we call displaced water. This is what we call displaced water. Okay? The more you submerge the object, the more water you get. Until you fully submerge the object inside the water, you will get an amount of water. Okay? Its volume equals to the volume of the object. Because this object displaces water, this water will overflow in the cup. The volume of displaced water equals to the volume of the submerged object. Also in the first case, the volume of this water equals to the volume of what? Of the submerged part of the object. Okay? This is called the displaced water. Its volume equals to the submerged part of the object. When we partially submerged the object, we found what? We found that it did not change, of course, 20 Newton. But the scale now measures 14 Newton. The scale measures only 14 Newton instead of 20 Newton. What does it mean? It means that there is an upward force equals to 6 Newton. What is this one? It's a buoyant force. So there is a buoyant force of 6 Newton. So if we leave the object to move down and to be fully submerged, what do you expect? I expect the buoyant force to increase. Why? Because all the volume will be submerged. And that's true. Here in the second case, the weight is 20 Newton. The scale here measures only 11 Newton. What does it mean? It means that there is an upward force of 9 Newton. We have 20 Newton in the weight, and it measures only 11 Newton, so the buoyant force is 9 Newton. Okay, so the buoyant force increases by increasing the volume or the submerged volume of the object. Until you fully submerge, if you move it down, nothing will change. If you move it down inside the water, nothing will change because you already submerged the whole object. Okay, guys? So let's go back and see what did Archimedes say about the buoyant force. A buoyant force on an object equals to the weight of the fluid displaced by the object. The buoyant force on a certain object equals the weight of the displaced fluid. Where is the displaced fluid here? It's the water in the cup. This is the displaced fluid. Its weight, if you can weigh it, if you find its weight, this is equal to the buoyant force. So the weight of this water equals to 6 Newton here, equals to the buoyant force. And the weight of this water here equals 9 Newton. The same like the buoyant force. Okay? That's what Archimedes found.
Doctor, I have a question.
Yes.
Is there a buoyant force in the air?
Yes. We said the buoyant force is for gas or liquid. Gas or liquid. Okay, and we will discuss that when we discuss the gases. You will find that the balloon is a good example for the buoyancy. Okay.
Okay. Another question, Doctor. So if we were in a vacuum room, it will be harder to lift a weight, right?
Yeah, because there's no air, so nothing will help you.
Oh, okay. Thank you, Doctor.
Okay. It's not gonna like there's. I don't think there will be a big change because air density is very low actually. Okay, so the buoyant force equals to the weight of the displaced water. Weight of displaced water. And the weight is mass times gravity. Mass of the displaced water times gravity. But I know that there is a relation between mass, volume, and density. We have just discussed it 5 minutes ago. We can say the mass of whatever object equals its density times its volume. Mass equals density times volume. So I will remove this mass and write it down. Density times volume. Density of what? What are you talking about? I'm talking about this amount of water. Displaced water. So this is the density of water. Whatever liquid you are talking about. If it is not water, it will be whatever oil or glycerine or whatever. What is the volume? Volume of what? Volume of the water in the cup, which we call the displaced water. But you told me 5 minutes ago that the volume of the cup, the water in the cup, equals the volume equals the volume of the submerged part of the object. The submerged part of the object. Yes. So can we write it? It's the volume of the submerged part of the object? Yes. So this volume is the volume of the displaced water, which is the same as the volume of the submerged part of the object times gravity. So this is the buoyant force. This is the buoyant force. It depends on what. Force gravity does not change. Okay, it's 9.8. If you are comparing the buoyant force for many objects in water, so water also is the same. So the point here is what the force depends on what mainly depends on how much volume is submerged inside the water, how much volume is under the water. Regardless the material of the object, regardless the shape of the object, it doesn't matter. What matters is how much volume is under the water. So let's look at this picture. We have two cubes. One is steel and the other is wood. Steel and wood. So the whole cube of steel has sunk under the water. It's now at the bottom. While the wood floats. So part of the wood is under the water and part of the wood is above the water. It floats. So my question is, which object of them is subjected to more buoyant force? Which one has more buoyant force on it? The wood or the steel? I'll give you a few seconds to think. Muhammad Al-Ghamidi says the steel. What else? I just said it 1 minute ago. It doesn't matter what the shape is. What the material is also. What matters only is how much volume is under the water. The more the volume that is submerged inside the water, the more the buoyant force. So if you look and compare the two objects, you will find that the buoyant force on the steel is higher than the buoyant force on the wood. Why? Because the whole object of steel is under the water, totally submerged, fully submerged. While for the wood, only a small part of the wood is submerged inside the water, so the buoyant force will be small force. But actually, you didn't answer the question because you are confused. Why are you confused? Because you look at, I said that the buoyant force on wood is very small, while the wood floats. And I said the buoyant force on the steel is high, while the steel sinks down. How is that? Because there is another factor. On each object, there are two forces. What about the weight of the object? The weight of the steel is much higher than the weight of the wood. And the weight is a downward force. Okay? So the weight of steel will be much higher than its buoyant force. So it will take it down. While the weight of the wood is small. So it will be in some kind of balance with the buoyant force. They will balance each other. Although the buoyant force is small, but the weight also is small. Okay, so the weight of the wood balances the buoyant force and the object health. So is there a method to know if the object is going to float or it's going to sink? Yes, there is. Look at the density data of the object. If the density of the object is less than the liquid, it will float. The density of the object is less than the liquid, less than the water, for example, it will float. If the density of the object is higher than the liquid, it will sink down. Give me an example. Yes. What's the density of water, guys? Remember, density of water? It's 1,000 kilogram per cubic meter. 1,000 kilogram per cubic meter. What's the density of wood? Generally, we can say density of wood is almost like 800 kilogram per cubic meter. So it's less than the water. That's why it floats. What about the steel? Density of steel is around 6,800, if I remember 6 or 7. I think 6,000. 6,800, but you can do it on the internet. Kilogram per cubic meter. Something around that. Okay? Density of the steel is around 6,800. So it's much higher than density of water. Okay? So that's why the steel sinks down while the wood floats up. So this is the method to know if it is going to float or sink. Compare it to the density of the fluid. Yes? So if you are in the air, somebody was asking about the air. If you are in the air, and you want to know if your object is going to fly in the air or lift up or what, you need to compare the density of the object to the density of air. If it has lower density than air, so it will float and it will move up. Like in case of the balloon that we have discussed at the beginning. Okay, this balloon, you fill it with hot air. The hot air has low density. Or maybe a balloon with helium. That's a good one, Muhammad al-Ghamidi. A balloon with helium. Okay. So if the density is lower than the air, it will float up. Okay. If the density is higher, it will move down. guys? So it's the same equation and the same phenomenon. If the object floats like this ship, what is the buoyancy? What is the buoyant force on the ship? The buoyant force on the ship is density of what? Rho Vg. Always remember that. Rho Vg. Density of water times volume of what? The submerged volume. Submerged. Where is the submerged volume? This part is the submerged volume. Okay. Times G, which is 9.8. This gives you the buoyant force. And this ship floats. So the two forces acting on the ship are balanced, which we in engineering equilibrium. Equilibrium means it is in. This is called equilibrium. So essentially the equilibrium requires what? Requires the two forces to be equal. Two forces are balanced. So the weight of the ship equals to the buoyant force. So I can say the weight of ship equals to buoyant force, which is rho times V times G. Rho of the water, G submerged volume, the object, G is 9.8. So let me make a problem so we can solve it. A ship has a mass 5,000 kilogram. Ship with a mass 5,000 kilogram is in the water. Find the submerged volume of the ship. Find the submerged volume of the ship. Find the volume of the ship under the water. Very easy. We have the equation here. The weight of the ship equals rho Vg. What is the weight of the ship? The mass of the ship times G. G equals the force rho of the water times the submerged volume, we call it P sub, times G. We can remove this G with this G. So the submerged volume equals mass of the ship, which is 5,000 kilogram, divided by rho. Rho is the density. This is a Greek symbol. Rho is a Greek symbol. Okay, which is 1,000 kilogram per cubic meter, and the result will be 5 cubic meter. So this is the volume of the submerged part of the ship, the part under the water. Guys, this is submerged. What is the buoyant force on a 0.9 kilogram ice floating freely in a liquid water? You have a cup of water, and a piece of ice floats on the surface of water. Its mass is 0.9 kilogram. That's why the iceberg, الجبل الثلجي, you can find it in the cold oceans or the cold seas. You might find an iceberg, big iceberg. And that's why if you know the Titanic ship, it sank because it hits what? It hits an big iceberg. Okay, why? Because the ice floats, okay, in the water. Okay, so if you have water, you will find an iceberg like this. Of course, not the whole object is above the water, but part of the object is above the water, and most of the object is under the water. Okay? But still, also, this is floating. Okay? So when you see a part of iceberg above the water, don't think that it's a small one. No, it's a very large one. But most of it is under the water. Anyway, it's also floating. Okay? Okay, let's go to our problem. We need to know the buoyant force here. Buoyant force. Buoyant force. What do you think? I know that the buoyant force in case floating, in case an object floats, where is it? In case object floats, the buoyant force equals what? To the weight of the object. Okay, so we will calculate the weight of the object, the weight of the ice, which is mass of the ice times g. Mass of the ice 0.9 kilogram times g 9.8, that gives you 8.82 Newton. So this is the buoyant force. Okay, I might ask you also how much volume is under the water. We will do the same like the ship. We will equate the buoyant force to rho v, rho of the water, v of the submerged part, g is 9.2. You can get the v. Okay? But here we didn't ask about it. The second part here is Pascal principle. Pascal principle. First, we need to discuss what the meaning of pressure. Pressure is a force exerted per unit area. So if you have a surface, and this surface it has an area 1 square meter, and you apply a force on the whole surface. Let's say you apply 1,000 Newton. So what is the pressure on this surface? The pressure is the force 1,000 Newton divided by the area 1 square meter. It gives you 1,000 Newton over square meter. Newton over square meter, we call it Pascal. So it's 1,000 Pascal. What if you decrease the surface? Let's say I will take another surface of an area 0.25, quarter of square meter. And then I will apply the same force on the surface, 1,000 Newton. So now what is the pressure? Pressure in the second case, the force, 1,000 Newton divided by 0.25 square meter gives you what? 4,000 Pascal. Okay? So by decreasing the area, you can increase the pressure. Okay? So if you apply the same force on a smaller area, that means you increase the pressure. Pascal, he studied pressure in the fluid, especially in the pistons, المكابس. So the piston is a tube that is full of a certain liquid, usually oil, usual kind of oil. We call it piston. He found what? He found that the pressure inside the liquid, or inside the fluid in general, transmitted throughout the fluid. Is transmitted throughout the fluid. So if we have this liquid here, the pressure at this point equals to the pressure at the other side. We called it here P1 and P2, pressure number 1 and pressure number 2. As long as it's the same fluid in the same tube, so the pressure on the left-hand side equals the pressure on the right-hand side. So what? We have just said that pressure equals force over area, right? So let's say the weight of the car is the force. I will call it F2. And the area of this piston, the area of the piston, I will call it A2. So the pressure is F2 divided by A2. The same for the left-hand side. I have the weight of the person is the force acting on the piston. The force of the person, the weight of the person is the force acting on the piston. I will call it F1. And the area of the piston is small here. I will call it A1. So the pressure is F1 over A1. Pascal said what? Said the two pressures are the same. So let's substitute. F1 divided by A1 equals F2 divided by A2. The force F1 divided by the area of the left side piston equals the force F2 divided by the right side piston. Okay? So what will happen? Let's say the two areas are the same. If the two areas are the same, what does it mean? It means the two forces are the same. It's normal. But what if the two areas are different? Like let's say area, the first one is 2 centimeters square, for example, and the other one is 10.
دكتور صوتك يقطع. الصورة راحت.
Now, you see it or not?
Yes, we see it now, بس الصوت يقطع. صوت تشويش.
Okay, let me see now. Okay, so let's say this ratio. Let's make it 2 square meter, and let's make it 10 square meter. Let's say F1, the force F1 is 1000 Newton. So what is the force F2 that's needed to balance the first one? What's the force F2? It will be 5000. That's a ratio. 5000 Newton. So if the ratios of the areas are 2 to 10, the ratios of the forces also the same. If the other one will be 5000 Newton. So you can increase the force using the hydraulic pistons. This is called hydraulic piston that has oil inside. We call it hydraulic piston. It's used to lift up some stuff. To lift up a heavy weight like the car. When you go to the mechanic, he uses hydraulic piston to lift the car up. Okay. What is the idea of this lifting? Using a certain small force, he can lift a huge amount of force on the other side because there is a difference in the area of the two sides of the piston. Okay. Let's try to solve this one. If a smaller piston has an area 1 square meter and a larger piston has an area 5 square meter, what would be the force that pushes the larger piston when a force of 100 Newton is applied to the smaller piston? So I have area here 1 square meter and area on the other side square meter. If you apply a force 100 Newton here, how much force should you apply on the other side to balance the 100 Newton? Pressure equals pressure. So force over area equals force over area. So 100 over 1 equals F2 over 5. So F2 is 500 Newton. Okay, 500 Newton. This is considered as a machine, by the way. If you remember the machines, this is considered as a machine. What is the mechanical advantage of this machine, guys? This hydraulic piston. What is the mechanical advantage of the piston? If you remember, output force over input force. What is the output force? I received 500 Newton and I did 100 Newton. So it's 5 times. 5 times. That's right, Muhammad Al-Ghamdi. It's 5 times. This is the mechanical advantage of this machine. Can this machine increase work, by the way? Can it increase work? Of course not. Possible. Okay, so the machine cannot increase the work. So if you want to lift, for example, if you want to lift this car upward a certain distance, if you want to move the car upward a certain distance d, so the work done on this side is what? Is the weight of the car, we call it the force F2, times the distance d. This is the output work. Of the machine. And what is the input work? The input work is the input force times, let's say, this part of the piston will move a certain distance L. So the input work equals the input force times the distance L. So this work cannot increase. The best scenario, what's the best scenario here? If this machine is perfect machine, if it is ideal machine, what do you think? the input work equals the output work. This is the best scenario if there is no loss. And that means the input force times a distance L, if you move down a distance L, equals the weight of this car, which is the force F2, times distance D. Okay? The force F input small, while the force F output is way big. So what about the L and the D? That means the L must be long distance and the D must be short distance. To equate the works on both sides, you have to move a long distance L to just raise the car a short distance D. Okay? And we are talking now about 100% efficiency, a perfect machine. If it has lower efficiency, the issue will be more worse. You will need to move longer distance to lift the car whatever shorter distance. Okay? Bernoulli's principle. I will need 5 minutes, guys. Bernoulli's principle. He says fluid velocity increases when the flow of the fluid is restricted. Restricted, like you try to prevent it or you try to limit the flow. Okay? Let's say we have a hose like this one. Hose. And water flows inside the hose. The end of the hose is A1. And the speed of the water inside the hose is V1. So there is something called the flow rate equals AV. The speed of the fluid times the area. This is called flow rate. معدل التدفق. The flow rate is constant. Through this tube must be constant. Let's say it's 1 liter per second. 1 liter every second. So if you inject from the faucet or whatever source, if you give 1 liter per second, how much will you receive on the other side? You must receive the same amount. You must receive 1 liter per second. Okay? So the flow rate through a certain tube is constant. If you give me 1 liter per second, you have to take it on the other side 1 liter per second. Okay? And the flow rate is area times speed. Okay. So if you try to restrict the output, on the opening of the hose, if you try to put your thumb or your finger at the opening, so you will decrease the area of the opening. You will decrease the area of the opening. So the area here is A2 is much smaller than the A1. What do you think will happen? What do you think will happen to the water? That's right. The speed will increase. So I expect the speed of the water to increase. Why is that? Because you have just said A1 times V1 is the flow rate, and your flow rate is constant. So it's also equals A2 times V2. If you decrease the area, you must increase the speed. And that's what Bernoulli said. Fluid velocity will increase. When what? When the flow is restricted. Yes.
When the temperature is increasing, the السرعة تنزل ولا لا؟
It's not part of Bernoulli's here. Temperature is something else. It has other effects. Okay.
Thank you.
Okay. So when the area decreases, the speed will increase. The second part of Bernoulli's principle, when the speed increases, the pressure that the fluid exerts will decrease. The pressure of the fluid decreases. Okay? So when you restrict the flow, area decrease the area. This will cause the speed to increase, and this will cause the pressure to decrease. Okay? There is a video here. I want you to watch it after. It's in the PowerPoint. You will find it in the PowerPoint. I want you to watch it after the lecture when you have time. Okay, that's a simulation. In this simulation, I have a tube. And I can decrease or increase the size of the tube. So I have a tube. The area here is A1, and the area here is A2. Okay? And I can measure the speed. The speed here is small speed, slow. So on the other side here, it's fast. So the speed increases when the area decreases. But the pressure is opposite to the speed. The pressure here is, as you see here, it's 102 kilopascal. Here it's 121 kilopascal. We don't need the numbers. What I need you to understand is the pressure here is high pressure. So when the speed is low, the pressure increases. When the speed is high, it will be low pressure. Okay? The last slide here is viscosity and Luzhuja. Viscosity is the resistance of the fluid to flow. If the resistance gives, if the fluid gives a resistance to flow, so we call it a viscous fluid. Like the honey. If you have a cup of honey and you want to pour it, is it easy to pour the honey? No, it's not, because it's viscous material. But if you have some water, a cup of water, it will be easier, because water has lower viscosity. Lower viscosity. Viscosity depends on what? The force of attraction between the molecules. You remember the attractive forces between the molecules? So it affects the viscosity. So how to decrease the viscosity? How to decrease the viscosity? If you remember the attractive forces, how to decrease the viscosity? By doing what? Do you know, guys? How to decrease the attraction forces between the molecules? Yes, excellent. By increasing temperature. So by increasing the temperature, this will lower the force of attraction between the molecules, and it will decrease the viscosity. The viscosity will decrease, right? So that's everything today. I hope you enjoy this lecture, and you can ask if you have a question.